Hello and welcome to lecture 12 of the course Complexity Theory. So in this will be a rather short lecture. I want to talk about some aspects of polynomial hierarchy that I wish to bring out, but that did not get emphasized in the previous one or two lectures. Okay, so we already know what is polynomial hierarchy, right? So what is polynomial hierarchy? It is starting from P, NP, CoNP, then sigma 2, sigma pi 2, sigma 3, pi 3, and so on, which I described in the previous lecture, right? It's this hierarchy of classes where and that there is a natural hierarchy that forms, and that is called polynomial hierarchy, right? So we have already seen uh, P and NP and CoNP. So NP, just to remind you, are the class of languages that have a deterministic polynomial time verifier, meaning to check L is a language in NP, then for all X that is in L, there is a short certificate and a verifier can verify the certificate, right? The verifier is deterministic. And if L is in CoNP, then there is a verifier, whatever certificate you give, it must be able to verify it, right? So X is in the language if and only if there is a verifier such that it will accept all the whatever certificate you give, it should be S instance. And even if one certificate is not validated, is not able to be validated, then it will be a no instance, right? So there is this asymmetry. NP means you just need one certificate to be verified. CoNP means you want all certificates to be to be verified. But even if one is not correct, then the language should not be in the language. Sorry, the string should not be in the language. And so here there is an existential quantifier in NP, and there is a universal quantifier in CoNP, right? And sigma 2, pi 2, etc. is taking this to the next step, and sigma k in general is k quantifiers, k alternating quantifiers starting with the existential quantifier, that is sigma k. Pi k is k alternating quantifier starting with the universal quantifier. Universal is for all, right? So we have up to k quantifiers, not up to exactly k quantifiers, but even if you have a subset of less than k quantifiers, that will be a subset of sigma k or pi k, right? That's what is shown in the figure here, right? K alternating quantifier starting with sigma is starting with their axis is sigma k, and for all is pi k, right? So now I want to bring out a couple of points. So one is that I mentioned that NP is a class of, or CoNP is a class of all languages whose complement is in NP. CoNP is not the complement of NP itself, it is a class of languages whose complement is in NP, right? Let me explain. So sorry, L is in CoNP, if and only if L complement is in NP, right? Suppose L complement is in NP, right? So then what can we say? If L complement is in NP, then there is a polynomial time verifier, which means if X is in L complement, right, there exists Y. So L complement has a deterministic polynomial time verifier such that length of Y is polynomial in the length of X, right? And there is a deterministic polynomial time verifier V such that, or maybe I should say this is not specific to the X and Y, right? Then there is a deterministic polynomial time v, okay, v is the verifier such that vxy is equal to 1. Right? So the v is just specific to the L complement. Now now consider so what about x that is not in L complement, right? So what is the negation of this? So suppose x is in L, right, which means x is not in L complement, right? X is in L complement, x is not in L complement. So even the right hand side we can negate. What is the negation of this? So I'm saying that there exists y is such that something is true. So the negation of this is there exists y such that something is true. So the negation of that statement is that for all y that is not true. Right? So it's like saying there are 10 students or 10 people, all of whom are right handed, or what do I say? Let's say there exists a left handed student in the class of 10 students. Right? The negation is that there is no left handed student, all the students are right handed. Right? So similarly, there exists a y with a certain property. The negation is that for all y, the property is not satisfied. Right? For all y such that y is in polynomial length of x, right, vxy equal to 0. That means this is the same verifier that as before, right? So now we have a deterministic machine that outputs 0 upon certain condition. Now I construct let's say set v prime equal to complement of v, right? So you can run the machine v and then flip the output. If it accepts, you reject. If it rejects, you accept, right? So that is v prime. Now I could write the same thing, right? For all y such that length of y is poly x, v prime xy is equal to 1. So x is in L. So again, I bringing out this here. X is in L if this is true. So now this is exactly the description of the class CoNP. Right? For all y such that y is poly x, vxy equal to 1. So here it's v is v prime. So it's another notation, but it is the same thing, right? So this is why this characterization makes sense. So if it's like satisfiability is like, does there exist a satisfying assignment? Tautology is the so if the assignment is not satisfiable, that whatever you plug in, everything evaluates to false. Now if I somehow complement the formula, right, I will get a new formula such that if the original thing was satisfiable, or if the original thing was not satisfiable, the new formula will be always satisfied. Right? So not satisfiable means it always evaluates to false. So the complement formula will always evaluate to true. So that's why if you take an instance, a Boolean formula phi, if it was not satisfiable, the complement of phi is a tautology. Right? So again, hope that adds some more insight to what I said in the previous lecture. Now let me just explain the same thing in the context of sigma 2 and pi 2, or sigma 2 is we'll say L is in sigma 2 if and only if there exists a polytime verifier, polytime V, deterministic polytime V, such that x is in L if and only if there exists y such that for all z uh, where y and, so I am skipping this part about y and z being of polynomial length, okay. We just for brevity, v x y z equal to 1, right. So now what about the complement of this? So let us try to negate the left hand side and right hand side. X is not in L, right, that is a negation of left hand side. So we want there exists y such that for all z this is true. So what is the negation of this? There is a y such that for all z something is true. So there exists y, so let us take it step by step. There exists y such that something is true. So the opposite is that the negation is that for all y that thing is false. So first step is for all y this thing is false. Now what is this thing? This thing is that for all z something is true. So now I want to negate that. So for all z something is true means that the negation is that at least there should be one z for which that is not true, right. So there is one z for which there is not true. So one z for which vxy should not be equal to 1. So now like we did before, I could define v prime in such a way that v prime of v prime is the complement of v. So v prime is 0 if v is 1 and v prime is 1 if v is 0. So now we can that means we can rewrite this as for all y that exists z such that v prime x y z equal to 1. So now we have that x is not in L, so we will say that x is in L complement is another way of writing the same thing if this is true. But now this is exactly the characterization of pi 2. So hopefully this gives you an idea why pi 2 is the co-sigma 2, right. So pi 2, in other words, pi 2 consists of all the languages whose complement is in sigma 2, right. So we took a language L which is assumed to be in sigma 2 and then we saw that the complement is in L complement is in pi 2. This is what we have shown. Again, hopefully this gives you some insight to the structure of the polynomial hierarchy. Similarly, I'll just use another color. Similarly, pi k is co-sigma k, right, because it's much of the same thing, right. You can do whatever we did for pi 2 you can do for pi k. So that is the first thing that I wanted to say. The second thing I wanted to say was about complete languages for sigma k. We saw NP completeness, we saw co-NP completeness. So let us see, does sigma 2 have a complete language, does pi 2 have a complete language, right. So the language that I want you to think about is what is called QSAT 2, right. QSAT 2 is a so QSAT 2 is set of all Boolean formula with designated partitions on the variables, okay. So I will have some variables as part of one set and some variables as part of another set. So it could be something like this, let's say x1 or x2 or y1 and x3 or x4, something like this, y2. So let's say a formula consisting of some x's and some y's. Now I want to ask this question: does there exist a way to set x's in such a way that, let's say, I get to set x, you get to set y. Now is there a way that I can set the x's such that whatever you set the y, it will be true. So can I fix some of the variables in such a way that, or there is some that is already demarcated to be my territory and given to me. Can I set some of the variables in such a way that whatever you set the remaining, the formula will evaluate to true. This is the language QSAT2. So the first class of the demarcated to me is denoted y1 here, right, and demarcated to you is given as y2 here, right, and I am asking, does there exist a way to set y1 is a set of variables here, okay, so it's a bit of a confusing notation, such that whatever you give to the variables y2, the formula will evaluate to true, right. So what is satisfiability in this kind of setting? Satisfiability is just there is no two player, only one player. Given this formula, is there a way to set variables such that it is true? Now it's like a two-player thing. I am given some variables. Now, is there a way to set these variables in such a way that whatever you set in the remaining, it will evaluate to true? So that is QSAT2. In other words, it's I think quantified SAT2. Q stands for quantified. Maybe I'll just write that down. Right, this is a bit messy, so I'll just write it again. Quantified set. Quantified means this there exists and for all are called quantifiers. Quantified set. And 2 means there are two quantifiers, right? And this is clearly in sigma 2 because there is a for all followed by this thing which can be verified by a deterministic polynomial time machine, right. So once you give y1 and y2 a certain assignment, it's easy to verify that the formula evaluates to true. And since and this happens to be this QSAT2 is a sigma 2 complete language. So again, we have not even defined sigma 2, but we can define it in exactly the same way that we defined an NP complete and CoNP complete. So what is sigma 2 complete? Just to define sigma 2 complete, sigma 2 complete so A is sigma 2 complete, A is sigma 2 complete if A is in sigma 2 and for all B in sigma 2, B reduces to A in polynomial time. So again, we use the same reduction, polynomial time reduction. So sigma QSAT2 is certainly in sigma 2 because it is of the correct form, and verifying that a formula at a given assignment is true is something that is achievable in polynomial time. And it is also sigma 2 hard, so to speak, meaning condition 2, anything in sigma 2 can be reduced to that, because consider any language L in sigma 2, okay. Now if X is in L, by definition there exists Y such that for all Z, the verifier has to evaluate X, Y, Z to be true. Now the point is that this verifier, whatever this verifier does, can be encoded into some Boolean formula, right? At least maybe a length specific Boolean formula. That means that I have already once instead of the verifier you have a Boolean formula, that is kind of the QSAT2 form, right? So that's why that is the intuition of this. So QSAT2 is a sigma 2 complete language. Similarly, you can define QSAT-K, right? So so just I will say a few more things. So QSAT2 complement is pi 2 complete. Just like we said, anything that is complement of NP complete is CoNP complete, we can say that anything that is complement of sigma 2 complete will be pi 2 complete. And similarly, we can define QSAT K, where we start with the existential quantifier and we have K quantifiers alternating. So here we have started with the existential quantifier in QSAT 2, right, and there are two quantifiers, there exists and for all, but in QSAT K we will have K such things, there exists for all, there exists for all, and ending in there exists or for all depending on whether K is even or odd. So QSAT K can be defined, and that will be the complete language for sigma K. This will be the complete language for sigma K, right? So if you want to show that QSAT like sigma K is contained in, let's say, a smaller class, let's say P, you can just show that you can pick QSAT K and show a polynomial time algorithm for it, a deterministic polynomial time algorithm for it. But again, QSAT K is something that is harder than SAT, right? Because SAT is just one quantifier, but QSAT K has K alternating quantifiers, and these are much more powerful, at least seemingly much more powerful, right? Finally, I just want to say one more thing, that this this polynomial hierarchy, it is so there are many levels, and as I said in the previous lecture, if let's say sigma 3 is found to be equal to pi 3, then everything above it will collapse to the level of sigma 3. If sigma 2 is found to be equal to pi 2, then everything above it will collapse to sigma 2 or pi 2. But it is believed that, so the thing is that we don't know if any of these are distinct. It is possible that all of them are equal to P. It's also possible that all of them are separate. Everything is different from every other thing. Sigma K may be strictly bigger than sigma K minus 1, which is strictly bigger than sigma K minus 2, and so on, right? So we don't know just like P versus NP, we don't know whether P is strictly contained inside NP or not. Any of this containment, we don't know whether it is strict or not, right? Because any of them, if any of them is proved to be equal, then many things collapse. So that's all I wanted to say in this lecture. So we saw why NP and CoNP are complement, or NP and CoNP, the characterizations in terms of the verifiers make sense. Basically, you take the characterization for NP and you take the complement of that characterization, you get the characterization for CoNP. And similarly, the same thing holds for even sigma 2 and pi 2 characterizations, and in general sigma k and pi k characterizations. Then we saw QSAT 2, which is a complete language for sigma 2, and generalized to QSAT k, which is a complete language for sigma k. And complement of QSAT 2 is a complete language for pi 2. And yeah, I think that's all I wanted to say in this lecture. And so we'll meet in the next lecture. Thank you.